Proszę.
Dzień dobry Państwu. Cieszę się bardzo, że tak trudna problematyka, jaką jest informatyka, fizyka, to seminarium odbywać się będzie właśnie w Ludzkim Towarzystwie Naukowym. Towarzystwo Naukowe, kilka słów o nim, powstało w 1936 roku pod nazwą Towarzystwo Przyjaciół Nauk w Łodzi. Niestety wojna przerwała funkcjonowanie towarzystwa. W 1945 roku ono odnowiło swoją działalność i przekształciło się w Łódzkie Towarzystwo Naukowe. Wobec tego Łódzkie Towarzystwo Naukowe jest kontynuatorem tego towarzystwa przedwojennego, międzywojennego praktycznie, które do dnia dzisiejszego działa. Znajdujemy się w tej chwili w siedzibie Łódzkiego Towarzystwa Naukowego. To nie jest oczywiście własność towarzystwa, ale Uniwersytet Łódzki nam udostępnił to pomieszczenie. Zajmujemy się, szeroko mówiąc, promocją wiedzy. Natomiast to jest najistotniejsze zadanie, jakie towarzystwo wykonuje. Liczy towarzystwo prawie 350 członków, samodzielnych pracowników nauki, czyli doktorów habilitowanych i profesorów. Działalność towarzystwa jest bardzo zróżnicowana, co nie znaczy, że ta działalność łączy się także z pewnymi komplikacjami. Mianowicie towarzystwo coraz trudniej jest utrzymać się w sensie ekonomicznym w obecnej współczesności. Prawda? Więc mamy wiele problemów finansowych, z którymi musimy w jakiś sposób walczyć. Nie wiem, czy to nam się uda, czy nie, ale tym niemniej ta sytuacja jest niewątpliwie bardzo trudna. Tyle może krótkich słów. Życzę Państwu owocnych obrad przede wszystkim i sukcesów, jakie by z tych obrad także wynikały. Dziękuję bardzo.
Dziękuję Panie Dyrektorze. Dzień dobry Państwu. Witam wszystkich na sympozjum Workshop on Quantum Hardware Software Systems. Więc tutaj celem tego workshop jest aktywacja ludzi mających potencjał w rozwoju technologii kwantowych w Polsce. I tutaj takim mottem przewodnim spotkania jest From Quantum Mechanics to Quantum Electronics and Quantum Software. No i tutaj będziemy mieli szereg prezentacji dzisiaj, które wprowadzą nas w tą tematykę. Więc tutaj zaczniemy od takiego nietypowego przedstawienia mechaniki kwantowej przez Quaterniony, po czym będziemy szli w stronę kwantowej metrologii, no i później oprogramowania kwantowego. Ostatecznie dzisiejszy dzień zakończymy prezentacją na temat nowych architektur komputera kwantowego. Liczę, że nasze spotkanie nie przyciągnie różnych fanów mechaniki kwantowej, fanów rozwoju elektroniki, czyli połączy tutaj jakby rozwój teoretyczny i rozwój eksperymentalny, no i w przyszłości da nam podstawy do rozwoju przemysłu kwantowego w Polsce. Mam zaszczyt Państwu przedstawić profesora Marka Danielewskiego, który nam opowie o Quaternionic Description of Quantum Mechanics. Professor, welcome.
I heard?
Go ahead.
Oh, voice is okay, eh?
Yes, go ahead. Yes, please.
Yeah. So I will speak about, instead of precise description, I will tell you a story how all this was developed, and will show you the very new results published few days ago. Everything what I speak today, you may find in publications. The last one will be available soon. Additionally, I show simulations done by Chantal Roth from Switzerland. With her, I cooperate since, let's say, 3 years or more. Time is running, difficult to say. Now, let's start. I will start from the very beginning. My first field, the activity that was even done with cooperation with your colleagues from Łódź, was diffusion equation. As you know, diffusion equation is the name of diffusion equation because of Fourier, and this diffusion is used to describe heat transport. Then this dot is the temperature, or concentration. Then this equation is called Fick equation, or vector velocity vector. Then it is Navier. In every case, of course, there are additional terms. Equation is three-dimensional, etc. But the fundamental is this second or first time derivative on the left, second order derivative on the right. Diffusion equation by Fourier. The curious thing that I have found, not during my study at university, but several years after, was that it is also related to quantum mechanics. When instead of dot you introduced the probability function and imaginary diffusivity, it became Schrödinger equation. Just multiply this equation by imaginary number and Planck constant, and you obtain Schrödinger equation for the free particle. So diffusion is basically everywhere. And in your body, everywhere there is electrochemistry. The key point in the electrochemistry is diffusion. Diffusion of ions, diffusion of potential, etc. Completely universal process in our universe. The question is, why this diffusivity is imaginary? Very fundamental question. Not, I would say, almost nobody understands why. This explanation that I will tell you today is not very popular. Becomes popular slowly. Answer is Quaternionic quantum mechanics. So let's switch. Beginning of my activity in this field, in science, was in fact diffusion. At several later after PhD, after habilitation, I switched. I was looking for interesting topic, and I was involved in interdiffusion. Interdiffusion means that, for example, when you contact two deep when you contact two different metals, they interdiffuse. Interdiffuse, they mix completely together. Ideal interdiffusion means that they are completely mixed together. So this is basically the simplest process. This problem was solved by Darken roughly during the Second World War. But my dream was 30, 40 years ago to solve this problem for multi-component systems. As many components as you want. Here you see interdiffusion, 3 component system, and experimental data. Continuous lines is simulation, dots show experimental. And then you look at the simulation of this process. What is interesting here, and is related to my talk, that you see this green line, it is uphill diffusion, so uphill diffusion. You may call this structure that is formed as diffusional structure. For those interested in solitons, for example, you see the kind of soliton. Knowing the theory, it's stabilized, and we can create this diffusional structure.
Professor, excuse me. We don't see your screen. There is some pattern which covers. We don't see anything on your slides.
Now?
I suggest you unshare and share again.
Now?
Oh, now it's okay. Now it's okay.
Sorry. So this is interdiffusion in 3 component system. The characteristic is, let's say, there's green line. Green line shows that initially uniform component, initially constant concentration. because of driving forces, chemical driving forces, forms diffusional structure. This looks like solitone in some cases. Knowing theory, we can stabilize this, etc. This was linked. Now I have to switch. Do you see this?
No, no, we don't see. You unshare your presentation somehow.
Yeah. Now it's okay, yeah?
Yes, it is.
So this uphill diffusion, this complex structure that are formed during interdiffusion, force us to ask the question: is there dynamics in diffusion or not? By dynamics, I mean velocity of local mass center, global mass center, forces, etc. Let's take a look at simplest diffusion coupling. Two different species, A and B. A is dense, B is less dense. So mass center is on the left. Mass center is on the left. Interdiffusion will cause that they will mix completely together. Now the question is this local mass center of this body constant or depends on time? If it depends on time, we have to give an answer why. We know that local mass center of this body depends on the position of one of the boundaries, let's say left boundary, and distribution of elements in the body. So, but the Newton's law says that because there are no external forces, the mass center should stay at the same position. So what must happen? In fact, during interdiffusion, with such diffusion process, boundaries must move. So diffusion will cause the movement of the body. Of course, process is very slow, but we are now speaking about the formal, mathematical, formal, elegant description of the process. And the formal, elegant description of the interdiffusion, in fact, any diffusion process, in many cases requires three boundaries dynamics. This was published by us several years ago, 1994, together with proof of existence and uniqueness of this formulation. So we have proposed the model with free boundary, and proof of uniqueness was published much later because of problems. Now, let's switch to a real topic today. This topic started with diffusion, published first time in 2007. Not many years ago, by the 25, yeah, not quite a lot, 25 years ago. Crystal. Why crystal? Again, you don't see this, yeah? No, I will skip it. I will skip it. So you shouldn't think that the crystal is the crystal that is deformed. The crystal is, whole universe is a crystal. Between the Planck distance, 10 to minus 35, and the size of the universe, everything is a crystal. This is the concept proposed by several people. This most serious approach was by Kleiner. When you open Google, Scopus, whatever, and you will ask questions, Planck crystal, Planck form, Planck scale physics, world, condensate, etc., you will find several works considering this problem. In fact, already Claire Maxwell in 1865 was thinking about crystal. Of course, during his life, even atoms were not recognized. So he couldn't think about the solid crystal. But in his in few pages that he has written about gravity, when in gravity, she said that he is unable to understand in what the medium, in what is a medium, and what is a medium that can possess such strong properties, and he is not considering seriously this proposition. But in fact, his explanation of gravity based on the postulate that everything happens in the medium, which is extremely dense. What is in complete contradiction, of course, to the vacuum, empty space that was completely accepted during his life. Yeah. With experience with interdiffusion, I got the taste, the smell of beauty of mathematics. You may say this like Feynman says. The real beauty of nature you understand when you can understand mathematics. In my case, I am not a mathematician, so I would rather cite Stephen Hawking, who wrote several times that equations are just boring part of the mathematics. So he thinks in terms of geometry. So our first attempt, the concept of Planck-Leibniz crystals, was born during work on diffusion. Because diffusion is the slowest process, we consider the situation with Kostek Holly, we consider a situation when there is huge mass, and such mass, of course, means high energy. During the high energy, defects are formed. You may say evaporate or emitted by the body in whole space. The situation is such simple only in the case when there is only one mass. When there is a second mass, such situation is unacceptable because in solids at constant temperature, without much stress, concentration of defects, whatever they are, linear or point defects, is roughly constant. So this is non-realistic situation. Situation looks more or less like that. Second body affects emission of defects from the first one, and creates, in fact, attractive forces between matter. This was the beginning of my understanding of gravity, very beginning. But of course, at the beginning, we were afraid. We didn't even think about considering there's a vacuum. Ether is a solid. From this first work, we predict gravitational constant, and that you see, this result is very good agreement with NIST. NIST is National Institute of Standards and Technology in US. It's the most precise physical data, in my opinion, that you can get. The agreement is almost perfect with our model. Now, in this picture, you see the Kleiner. Hagen Kleiner, I met 5 years after this first work was published. He was in Berlin, Freie University in Berlin, and because he is the author of the concept of world crystal, first, you see him. This is the picture here is in fact Swarovski world crystal, real crystal. He really enjoys this. So the third element, so to what Kleiner did, I have had seminar in his group, unexpected seminar, and during the seminar I was telling more or less the same things like you have heard already, and I expected that Kleiner will prize my concept of gravity, or no, force field, blah blah, etc. Equations. But he prized me, he mentioned only one concept from the old work, previous work, imaginary potential, complex potential. Because to obtain the Poisson equation for gravity, I postulated existence in the crystal, imaginary potential, with the real part, which speaks about deformation and creates gravity, and torsion, twist, which is imaginary part. This twist creates, for example, Maxwell equations, etc. So, in fact, in 2013, we, because then I was working with colleagues, we have entered a new path, Cauchy. No diffusion and no dissipation. Ideal, elastic continuum. Ideal. Of course, many people ask why we did not consider Navier, which is, $1 million is still waiting for the mathematician who will be able to prove of existence and uniqueness of this equation. Navier system is used in liquids, gases, in almost every technology. It is important, is Navier problem. And proof of the uniqueness and existence of solutions is done only for the short time periods only. Then I found that elegant mathematical well-posed equations are done by Cauchy 1 year later. With my experience with mathematics, I just felt that it would be much more safe, if not much more effective, to use well-posed equations by Cauchy. Cauchy means ideal elastic crystal. No defects, no diffusion, nothing, just pure elastic crystal. Is there such medium? In some. In reality, of course not, unless you say universe is ideal elastic crystal. So now, with this 3 elements, we could go from the displacement vector in Cauchy theory to deformation quaternion. Now I will speak to you then. Now I may call this ontology of quantum mechanics, because in fact, if you accept such medium, such explanation, you will understand quantum mechanics. You will understand. So element 1 of this ontology is Planck-Kleiner crystal. Why Planck? Because additionally to the model of ideal elastic crystal, Cauchy model, at the Planck scale, I have assumed that properties of this crystal are described by Planck numbers. Planck distance, size of elementary cell, Planck mass of this elementary cell, and velocity of light related to energy of this continuum. Second element is Cauchy model. Cauchy model, here you see Cauchy, very serious man. One of the best mathematicians, by the way, or famous mathematician. And his equation of motion. This equation of motion relates acceleration with force. There are two ingredients of force. Divergence of vector, velocity vector, this is related to compression, and twist, rotation of displacement vector, twist in this ideal elastic continuum. Of course, this equation is in three-dimensional space. Cauchy equation of motion. Now, stimulation by Kleiner. Kleiner remarked that my most important problem in this first work was imaginary potential. After many years, after not very long time, stimulated me to think why complex number if our space is three-dimensional. So what is the imaginary description of three-dimensional space? And then I have found, I recognized quaternions. Only quaternions. There is no escape from the quaternions problem. Never before I knew quaternions. I never read anything about quaternions, but roughly 15, 20 years ago, I realized that to get better description, we need to introduce quaternions. So incorporate third element of this ontology of quantum mechanics, I call this now quaternion quantum mechanics, is non-communicative, it's Hamilton algebra. Hamilton algebra, everybody knows imaginary number. Square of this is -1. Without going into the details, Hamilton postulated and developed the algebra when there are three imaginary components, and such a rule, of course, several others, is based on quaternion algebra. This was very famous, and you may find this on Brougham Bridge in Scotland, written in 1843. So, I will not go into the details. Transition or operation, everything what I said is has strict mathematical base. So in publications, all derivation can be found. You may verify, check, and try to understand. The basic transition is from the Cauchy elastic continuum, and then Helmholtz decomposition theorem. This Helmholtz decomposition theorem states that under certain, in ideal elastic continuum, this decomposition is valid. So every displacement vector can be split into the twist part and compression part. Everyone. This implies that there must exist something, because Cauchy theory is well proved, well taught, that can be the variable can be formed the superposition of compression and twist. So using the quaternion algebra, we can go from the vector equation in three-dimensional space, Cauchy original equation, to the quaternion formulation of Cauchy equation of motion. So this is exactly the same. You can go in up and down without any restriction. The only restriction here is that I mentioned is that divergence of rotation is 0. In fact, this is very common in almost everything. In many fields, the divergence of rotation is 0. So we have two equations in three-dimensional space and four-dimensional space. Is it shocking? Not really. Example here is in fact already told by Hamilton during his age. There is analogy between time-space continuum and quaternion, the formation quaternion here. Now, of course, you may look at this, that there is analogy between time and compression, but this analogy is even seen in equations. Cauchy-Riemann derivative of this gives solutions in three-dimensional space. So there is, but I will not go into this detail. But it should be not shocking that we have to use, which is convenient to use, very profitable, to use quaternion to describe deformation in the simplest solid that is possible. Simplest. Because ideal elastic solid is in fact the simplest solid value. So now let's open Pandora box. This equation, quaternion formulation of equation of motion, displacement quaternion and compression part, allows for multiple forms of formation of multiple waves. I will finish this lecture showing you quarks. So it can be applied in quantum mechanics in general. Why it is possible? Again, simple explanation. Cauchy equation of motion in three-dimensional space in fact, can be looked at as a compression and twist. Sum of this is Cauchy equation of motion in three-dimensional space. Quaternion formulation of the Cauchy equation in four-dimensional space looks like that. But what is because of mathematics, because of using quaternion algebra? It's like this is quaternion algebra, it offers the real number. What is a real number necessary in physics? Energy. So using the quaternion algebra, we can cut energy for any pieces that we want and create new species. For example, from the given energy, we can create equations describing the crystal. Why not? If this is correct, we can do everything. Quaternion algebra allows us to analyze completely different configurations, complexes of energy. Let's start with simple case. Again, quaternion formulation of equation of motion. We can split this into two equations. In fact, by postulating existence of such term. This postulate is possible because of Planck scale. At the Planck scale, in the elementary volume of the crystal, coupling between transverse and longitudinal wave may occur. So we may write this. If you write something like that, you will see that this equation is in fact quaternion Klein-Gordon equation, Klein-Gordon type equation in the quaternion form. This was published in many years ago in the paper, and here on this you'll see the numbers that are obtained using such phenomenology, such theory. The numbers for this idea, for this Planck-Kleiner crystal are really strange. Volume of elementary cell, 10 to minus 100. Planck density, almost 10 to 100. Young modulus, more than 10 to 100. Planck mass mobility, relatively low, but when you look at the numbers, it's relatively high. Now, interesting output of this is in agreement with National Institute of Standards data, so many computed from published data, with one, of course, remark that nobody considered seriously such continuum. Now, the result of the theory of the model, you see the computed Planck constant and Planck constant by NIST data. Agreement is perfect. Gravitational constant you have seen all right. Gravitational constant was already, so I showed you already, speed of longitudinal wave higher than speed of higher. And speed of light, again, in very good area. Now, next step. Different equations. Schrödinger equation is slightly strange because it has first order derivative on the left and second order derivative on the right. It's in fact a diffusion equation, so it's not relativistic. But it's very convenient in chemistry and in many areas when the velocity of the particle, velocity of the whatever we analyze is not important. Then Schrödinger equation is very profitable, it's very interesting. So we can, I will show you the schema for obtaining Schrödinger equation. When you look at this equation shows and this term in the bracket is energy density in the ideal Cauchy elastic continuum, computed from his equation of motion. So as elegant formula for energy. Additionally, there is external potential that we can assume, of course. So what is the problem in this? This is not in fact equation, because it contains unknown function, velocity. We don't know velocity. Velocity might be computed for the equation of motion. At this moment, we don't know it. But what we can do, Cauchy-Riemann derivative is an answer. The normalized velocity, normalized means local velocity that is divided by the wave velocity, speed of wave velocity, is the Cauchy-Riemann derivative multiplied by Planck length. When we introduce this and use the experiment principle, we can, from energy density, introducing the Riemann gradient of Quaternionic potential, obtain the real functional, and minimizing of this food functional leads to Schrödinger's stationary equation. So you see, instead of velocity, we introduce Cauchy-Riemann derivative, introduced the probability function, which means, in fact, you may have normalized energy density, maybe cost, and minimizing this leads to the stationary Schrödinger equation. Another test of this theory. Minimizing means it is proved. So by using mathematical rules, no other assumptions. From the energy integral for energy of the particle, we can obtain Schrödinger equation for this particle. Now, I have to skip because time is running out. So I will show you now the real results obtained very recently.
Professor, you can talk till 2 o'clock. You have still 20 minutes.
Yeah, but you may have 1 or 2 questions. And so, this last work now submitted for publication is Quaternionic quantum mechanics 3, baryons, quarks, and their Q potentials. The basic properties of quarks in baryons. There are 3 quarks, UCT, quarks, and there is group of down quarks. Charge all of them in group are the same, and spin is always everywhere is 1 over 2, 1, 2. So now, this theory, the careful analysis of data, it's difficult to answer how I did it. I may say careful analysis of the data and analysis of the symmetry of equations allows to postulate a system of equations for, let's take a look, for the down quark, and system of equations for the up quark, U and D. How this can be verified? Well, if proton is formed by 2 down up quarks, we just multiply this system of equations for the up quark by 2 and add this to the down quark, and this sum should give us equation for the proton. When you do this, it is relatively simple. Mathematics is very simple. So this way, you see the system of equations for proton. Now, what you can note? You see that in the quark down, we should expect charge minus 1/3, and this is related to propagator in this system. In the down quark, the charge is 2/3, and you see this here. Spin, I did not analyze the spin problem, but symmetry again shows that in both cases spin should be 1/2. Now, the result is, I'm going to change that. Yeah. The result is proton. What is characteristic for what should we expect for the proton? For the proton, we should expect combination of the scalar potential and vector potential, because there is a charge and gravity, Marker mass. And you see that potential equation, Poisson equation, argument of Poisson equation is quaternion, contains scalar part and vector part. So this confirms that this reasoning is correct. It might be real that we have found the proper equation system for up and down quarks was found. This may be verified for neutron as well. Neutron, according to data, contains two experimental evidence, and in fact, a physical theory as well. Neutron is formed by two down quarks and one up quarks. So we can do the same operation. Add two down quarks with one up quark and obtain what we have obtained. We in fact obtain slightly modified Klein-Gordon equation. Also, no electron charge, only gravity. Only gravity is present. Gravitational potential is generated. Now, comments to this. You see, another interesting is the result that I didn't have time to show you too much, but too much is not always a very good solution. That all previous equations, proton, neutron, electron, they fulfill one condition. They can be transformed to original Quaternion formulation of the Cauchy equation of motion. This might be sign of stability of those equations, stability of those particles. All systems for that I have studied, electron, neutron, proton, Klein-Gordon, all those equation systems, when you reduce them, it becomes that the Quaternion formulation of the Cauchy equation. It is not true in case of systems for U and D quarks. They do not meet the relation with the Cauchy equation of motion. It might be mentioned that also experimental efforts to find the individual quarks were without success. Physicists were not successful in isolate quarks. They are observed always as a bound states of three quarks form baryons, and quark and antiquark forms the mesons. Wilczek, Nobel Prize winner several years ago, in his Nobel Prize lecture and in several words, calls it phenomenological paradox. Quarks are born free, but everywhere they are in chains. You see, inconsistency of quarks, partial differential equation that I have shown you a while ago, with quaternion forms of the Cauchy equation of motion, might account for the observed quarks, chains. Separated are not stable. When forms a quark chains, they are more stable, and they are observed. Quarks chains are observed in reality. Now I want to show you some, at the end, I will show you some simulation. All simulations were done by Chantal Roth. She is very good in this, but I must switch now because apparently
Do you have anything more to mention, Professor Danielewski, or do you await the questions right now?
I will switch very fast.
Okay.
What you do.
maybe in meantime, if you have some questions.
Oh, yes, it's something.
Is it okay?
Yes, it is. There is one question from the audience. Can you accept the question?
Yeah, of course.
But I'm not sure if you hear me, Professor? Oh, okay, I can come here. Okay, so I have a question about these quaternions that go into quantum computing, which is the topic of our meeting. I found a number of papers. Well, first and foremost, I knew quaternions because I had a history in my life of writing 3D objects, okay, in games and things. So quaternions I used to describe in games, right? It's a very good tool. But in quantum computing, there is a small number of mentions, tiny little number of papers. There is one famous paper, Quaternion Computing, by the way, Fernandez and Schoenberg, something like that. But for me, it's unimaginable, but you know, I was not practicing quantum computing for many years. So tell me, Professor, why the problem I see is so horrible? Quaternions are not commutative, right? I mean, if you take the standard complex numbers on which we base Hilbert space, they are commutative. I mean, saying numbers, okay, I'm not saying the operators, but quaternions are not. So I really cannot imagine how you could create, you know, the analog of Hilbert space even, where your basic scalars, okay, which are these quaternion scalars, are not commutative. So what is the real value of that for quantum computing?
For quantum what? Quantum physics?
Quantum computing, which is the main
Computing.
object of why we discussed that here, I believe, right?
In our paper about, in our first paper in entropy, you will find the answer.
I see. Okay.
The Sobolev spaces and all this can be obtained. So there is no problem with space in using this quaternions in computing.
Okay. Well, but how to handle this case that you have scalars that are not commutative? If you could say, just, you know, figure out.
Excuse me, I do not understand. What?
How you handle non-commutative character of quaternions when they, in the formulation of computing, replace complex numbers? Because that's what maybe I make a wrong I don't know, positioning or putting them in a wrong. I don't understand that.
As far as I know, in physics, it's a complex number. When you deal with complex numbers, you in fact deal with two equations: real part and imaginary, etc. In quaternion algebra, you have four equations, four scalar equations instead of two. Why this is now? What is the analogy between this? In fact, three twists in quaternion algebra forms one twist vector. But this twist vector is rotating in space in every direction. So in fact, three twists in quaternion four-dimensional space can be in several situations can be simplified to one twist in complex algebra. Again, complex numbers for algebra, so everything is okay. Now, reality is much more difficult, much more complex. That's why quaternions are so effective. And what you have seen today, as far as I know, nobody ever wrote the equations for quarks, as far as I know. So quaternion algebra offers much more possibilities, can describe much more complicated systems. In quantum mechanics, to get progress, in fact, quantum mechanics is called by many operational quantum mechanics, because they introduce operator, new phenomena, new problem, new operator, very often. I do not follow this exactly, so no, I cannot tell much more about this.
Right.
Perhaps what has been done is due because I didn't know the operator algebra. And I was not afraid to start this from the different point of, from the different starting point, because starting point was really three-dimensional diffusion equations, three-dimensional, and from the three-dimensional problems we switched to the quaternions.
Okay, I must
I'm not sure if, but remember, you will find the mention about mathematical problems, computing, in one of the works that I listed at the beginning, Ontology of Quantum Lines. You will find this.
Okay, I will try. Thank you. Thank you. Anyway, I need to consume that because at face value it's hard for me to comprehend that. But thank you very much. Okay.
Yeah. Do we have our questions from students? Yeah, so there is some simulation you want to mention. Go ahead. Yeah.
Yeah. Do you see simulations?
Yes, so we can follow we see everything. Yeah.
Yeah. So now you see simulation done by Santandro, pin 1/2. And another one. On this simulation, it is shown, this is just a reference board. Let's just to visualize this. This is simulation of it was pin 1/2. Now you have simulation of two particles with 1, 2 spin. They interact together. Again, in fact, in real situation, this ball should compress and expand. But to simplify the problem, it is only expanding. Different direction of the spin. You see interaction between two particles with spin 1/2. Yeah. That's it. Yeah. Do you see now?
Yes, we see everything. Yes.
Yeah.
Yes, we do.
Yeah. Okay. Is presentation on the screen?
Yes, everything is on the screen, right?
So what I have shown you, I was showing you that processes at the Planck scale related to our to us as humans. Now, of course, there are only questions. Don't think that everything is answered. No. It's a very, very interesting question. Is there anybody in anything between? I mean, what do I mean by between? Atoms and nucleus are in the range of 10 to minus 10, 10 to minus 16. Are there other, let's say, worlds between 10 to minus 16 and 10 to minus 35? The same I might be asked for the large scale between 10 to 10 and 10 to 30, let's say 10 to 20. Is there anything there? Even more interesting question. Is there the question, by the way, asked by Feynman. Is there anybody down there? Is there anything down there below Planck scale? There is no reason to say no. So let's say, for me personally, myself, I do feel quantum mechanics now. I know that everything is a wave. Atoms, protons, quarks, everything is a wave. This wave interact, they form bodies in biology, they form atoms, they form planets. Everything is just a wave. At this scale, there are bosons because charge is compensated during the huge mass. At this scale, again, almost everything is bosons dominate. So you may feel this. Everything is a wave. But Is there anything between? Don't say. Physical reality at the Planck scale. You see, such a models show you that faster than light velocity, the faster of light velocity is, for example, longitudinal wave. And of course, faster than light velocities are possible in Quaternionic quantum mechanics. They are possible. Kleiner, in his first paper, wrote that fine tuning is necessary to make all sounds equal. In my opinion, he wrote this because he wanted his paper to be accepted for publication. His real thinking was almost for sure different. There are possible faster than light velocities. There are possible pre-Planck particles. Energy associated with atoms, quarks, is very low. So this will not, it's not possible to create this energy to create defects in the sense of solid state chemistry, let's say interstitial Planck particles, like in solids. But at very high energy, there are possible. By the way, the probability of such particles, of course, is non-zero. This might be related to dark mass and dark energy. The collective behavior that I was showing during my lecture of the Planck particles is in fact related to the particles, quarks, and the stationary waves. Stationary in case of particles, less short living times, quarks, etc. Final remark. I think much of you is engaged in more the everyday work. It is definitely exaggeration, but you should realize that in fact, Planck crystal and all of I have presented here is almost straightforward. If you spend some time, I learned about quaternions 15 years ago, first time, never before. Of course, I did not understand. The complex numbers were completely zero. But you see the stage at which we are now with my coworkers. But now compare this complexity of physicochemical processes in multi-component systems, diffusion interdiffusion problem, but then you really saw if you have grain boundaries, you have defects, effect of stress, effect of temperature gradient, complexity of physicochemical processes in reality is in fact much more higher than in quantum mechanics, much more higher. It's the same it may be told about the measurements. You cannot measure diffusion directly in any medium. Why solid was interesting? Solid offers one interesting possibility. Interdiffusion occurs at high temperature. You can cool the solid down and observe situation which was done after the heating period. You cannot do this in liquids and gases. Observed diffusion is almost like, it's even more difficult in quantum mechanics. There's not much difference in because, of course, when you speak about precise data, precise numbers. So that's the end. I can answer many questions. But one explanation, one more remark. The mathematics of this is done. All mathematics was corrected by Lucian Schaffner, who is a mathematician, and he learned quaternion algebra as well. So now he's checking all my calculation computations. Simulation are done by Chantal Roth from Switzerland. She's obviously she's very good in computing. Thank you for your attention.
Thank you for the presentation. Do we have any questions maybe from the Zoom audience? Is there anybody with a question? Do we have any question from this room? If not, okay, thank you, the speaker again. And our next speaker is Konrad Norowski and Professor Maciej Zgierski from Polish Academy of Science, Institute of Physics. The title of the talk is The Fastest Thermometer in the Nanoworld. Welcome, Konrad Norowski, welcome.
Yeah, am I being heard? Can you hear me?
Yes, we hear you, but Professor
Okay.
Danielewski, can you unshare your presentation? Yeah, just, all right, and please, Konrad Norowski, please share your presentation. Maybe I will
Can you
just.
see it?